Tonight, we're going to look at something that seems calm and distant, but could change the world in a single moment. A global supervolcano. You've probably heard the word volcano many times before. Scientists talk about them often when they explain how Earth works. But here's what most people don't realize. When you truly understand what a supervolcano is, when you grasp the scale of an eruption like this, it changes how you see life on this planet. This is not just a mountain with lava. It's a force so powerful that it can affect climate, food, and survival across the entire world. And by the end of this journey, you're going to understand why scientists take this threat seriously, and why preparing for it is far harder than it sounds. Before we go any further, if you enjoy slow, deep explorations like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. A supervolcano is not simply a larger version of the volcanoes people see erupting along mountains or near ocean coasts. It is a rare geological formation, defined not by height or lava flow, but by the scale of its potential eruption. Ordinary volcanoes erupt with lava and ash that affect local regions. Supervolcanoes, by contrast, have the capacity to release more than 1,000 cubic kilometers of material in a single eruption. This is thousands of times larger than typical volcanic events, capable of altering the climate and reshaping continents. The physical structure of a supervolcano differs from the conical peaks of common volcanoes. Many do not have the familiar pointed summits. Instead, they form vast calderas, broad depressions caused by the collapse of land following the emptying of an enormous magma chamber beneath the surface. These calderas can span tens of kilometers in diameter, so large that from above, they appear as subtle changes in landscape rather than towering mountains. Within these calderas, heat from magma continues to shape the ground. Fumaroles release gases, hot springs bubble to the surface, and minor eruptions of steam and ash can occur without warning, signaling the presence of an immense reservoir beneath. The magma beneath a supervolcano is unlike that of smaller volcanic systems. It is thick, viscous, and rich in silica. This composition traps gases within the molten rock, preventing them from escaping gradually. Pressure builds over thousands or tens of thousands of years. When the magma finally finds a path to the surface, the result is an explosive release of energy and matter. Unlike lava flows that move slowly and can be avoided, a supervolcanic eruption can emit pyroclastic flows that race across the landscape at hundreds of kilometers per hour, carrying searing hot gas, ash, and rock fragments. Historically, geologists have identified several supervolcanoes that illustrate both the power and potential consequences of these eruptions. Yellowstone, located in the United States, sits above a massive magma chamber. Evidence from the last three eruptions occurring 2.1 million, 1.3 million, and 640,000 years ago shows vast ash deposits stretching across continents. Another example, Lake Toba in Indonesia, erupted approximately 74,000 years ago, producing an ash cloud so extensive that it affected climates worldwide. Taupo in New Zealand offers a more recent example of a supervolcano that reshaped the surrounding environment, leaving deposits hundreds of meters thick over a wide area. Scientists study supervolcanoes by examining these geological records. Layers of ash in soil and rock reveal the timing, magnitude, and spread of past eruptions. By measuring the chemical composition of ash and pumice, geologists determine the nature of magma, the pressure it held, and the force of the eruption. Modern instruments allow continuous monitoring of heat flux, ground deformation, and gas emissions, providing clues about how a supervolcano behaves beneath the surface. GPS sensors track shifts in the Earth's crust, indicating the slow movement of magma, while satellite imaging reveals subtle changes in elevation over the caldera. Supervolcanoes often remain dormant for tens of thousands of years. During these periods, activity is not absent, but exists in minor forms. Steam vents, small geysers, and earthquakes hint at the restless nature of magma. These signs are essential for scientists who study supervolcanoes, because even a small change in pressure or composition can indicate a shift toward a more dangerous state. Understanding these subtleties is critical. The immense scale of a supervolcano means that when it eventually erupts, the effects will not be limited to the immediate area. Ash can circle the globe, and the release of gases such as sulfur dioxide can change the climate for years. The sensory experience of being near a supervolcano is unlike any other. In places like Yellowstone, the smell of sulfur hangs in the air, and hot steam rises from fissures in the ground. The heat of the earth is palpable, even through snow or forested land. These signs are gentle reminders of the immense energy stored below, a quiet prelude to potential violence on a scale that humans rarely witness. Ash clouds from past eruptions have left layers visible even today, pale grey and fine, like powder spread across distant valleys. Rocks and pumice scattered across the landscape tell a story of force and magnitude, silent evidence of Earth's capacity for sudden, dramatic change. Supervolcanoes are also associated with a range of secondary geological effects. As magma moves upward, it deforms the surrounding rock, creating fractures that can cause earthquakes even when no eruption occurs. Heat can alter the chemistry of nearby rivers and lakes, increasing acidity or releasing minerals that disrupt ecosystems. The slow expansion of magma chambers can uplift the land, changing river courses and influencing vegetation patterns. All of these subtle changes occur long before any eruption, demonstrating the continuous influence of supervolcanoes on their environment. Despite the fearsome potential, supervolcanoes also play a role in Earth's long-term geological and biological processes. The ash and lava they produce enrich soil with minerals, fostering plant growth over centuries. The deposition of volcanic material creates new landforms and contributes to the cycling of elements essential for life. Even the release of gases into the atmosphere, while disruptive in the short term, has shaped Earth's climate and composition over millions of years. These processes underscore the dual nature of supervolcanoes: destructive yet formative, catastrophic yet essential to the planet's evolution. Monitoring and understanding supervolcanoes remains a challenge because their cycles span geological time. Human lifespans are brief relative to the timescales on which magma accumulates and pressure builds. Scientists rely on models, historical evidence, and modern monitoring to anticipate future behavior. These models incorporate heat flow, magma chemistry, crustal strength, and seismic activity to provide estimates of eruption likelihood. While precise predictions are not yet possible, the data allows for risk assessment and preparation, illustrating how careful observation can provide insight into phenomena that otherwise seem unpredictable. Ultimately, the study of supervolcanoes begins with recognizing their scale and potential. They are not threats that announce themselves in dramatic lava flows visible from a distance. Instead, they are vast, often subtle forces beneath the surface, accumulating energy over millennia. Their eruptions, when they occur, reshape landscapes, affect climates, and challenge the resilience of life on a global scale. Observing them requires patience, meticulous measurement, and an understanding that Earth's most profound transformations often happen silently, hidden beneath layers of rock and soil, waiting for the moment when immense power is released. Beneath the Earth's surface, a supervolcano begins its long, slow preparation in silence. Magma forms deep within the mantle, where heat and pressure melt rock into a dense, molten mixture. This magma is thick and sticky, rich in silica, and moves slowly through fractures in the crust. Over tens of thousands of years, it collects in a chamber far below the surface. Each new pulse of molten rock adds to the pressure within the chamber, slowly deforming the surrounding rock. The ground above rises imperceptibly, and minor cracks appear as the crust stretches and bends under the strain. As magma accumulates, gases trapped within it create tension. Carbon dioxide and sulfur dioxide dissolve into the molten rock, held prisoner by the surrounding pressure. This gas buildup is crucial. If too much pressure is released slowly, small eruptions may occur, venting steam and ash without a major explosion. Yet if the pressure continues to rise over millennia, the rock above the chamber weakens, reaching a critical point. When this happens, the magma will find a path to the surface in a violent, unstoppable rush. The eruption itself unfolds in stages. First, minor vents may open around the caldera. Steam escapes, carrying fine ash and gas into the air. These initial events are deceptive. They appear small compared to what is about to come, yet they relieve only a fraction of the immense pressure. As the chamber fractures, the main vent breaks through the crust. Magma explodes outward, propelled by gas expansion and pressure release. Pyroclastic flows surge across the land at incredible speed, consuming everything in their path with heat and force that can exceed several hundred degrees Celsius. During the main eruption, ash and rock fragments are hurled into the atmosphere. Plumes rise tens of kilometers above the surface, forming towering columns that can be seen from hundreds of kilometers away. The ash is fine and abrasive, falling slowly in distant regions, blanketing landscapes and darkening the sky. Along with ash, gases like sulfur dioxide and carbon dioxide pour into the atmosphere, interacting with sunlight and weather patterns. Sulfur forms tiny particles that reflect sunlight, leading to drops in temperature, while carbon dioxide contributes to longer-term atmospheric changes. These emissions can last for months, spreading globally and altering weather and climate in measurable ways. The chemical composition of the eruption is as important as its force. High silica content in magma makes it more viscous, trapping gas and leading to more explosive eruptions. This viscosity prevents magma from flowing smoothly, so when it breaks free, it does so violently. Alongside molten rock, fragmented stone and ash, the eruption releases toxic gases. Sulfur dioxide forms acid rain when it combines with moisture, affecting rivers, soils, and vegetation. Carbon dioxide, while less immediately harmful, adds to greenhouse gas levels, influencing temperature patterns over longer periods. Tiny particulates remain suspended in the atmosphere, scattering light and creating hazy skies that can dim sunlight for months or years. The visual effects during an eruption are extraordinary. Ash clouds rise like dark mountains in the sky, dense and opaque. Lightning often flickers within the clouds, caused by the friction of ash particles rubbing together. Rivers of molten rock flow slowly but relentlessly, consuming forests, roads, and towns. The landscape vibrates under the force of explosions, and distant tremors alert those far from the caldera to the violent activity below. Even after the main eruption subsides, clouds of ash drift across continents, creating twilight in the middle of the day, coating buildings and plants in grey dust, and turning snowfields into dark, ashy expanses. Eruptions are not uniform in their intensity. Some regions closest to the caldera face immediate devastation from pyroclastic flows and lava. Farther away, ashfall is the main hazard, sometimes accumulating meters deep, crushing structures and smothering life. The combination of heat, pressure, and falling debris reshapes rivers, valleys, and plains. Lakes may be drained or created, mountains eroded, and soil layers altered. These changes are permanent, visible long after the eruption ends, and they document the immense energy that once moved through the earth. Magma movement before an eruption affects more than just the eruption site. The pressure within the chamber can trigger earthquakes hundreds of kilometers away. Rock layers bend and crack, causing landslides or small tremors that serve as warning signs to scientists. Heat rising from the chamber may alter local groundwater, creating new hot springs or geysers. Even minor gas releases can change the chemistry of nearby lakes, affecting ecosystems and signaling the underlying activity. These subtle effects are part of the broader picture, demonstrating that a supervolcano influences its environment long before a dramatic eruption. The aftermath of an eruption begins immediately. The land near the vent is buried under hot ash and pumice, while distant areas experience ashfall that can last days or weeks. Airborne particles reduce visibility, and the sky darkens for months in some regions. Rivers become clogged with sediment, affecting water supply and aquatic life. Plants are destroyed, animals displaced, and human settlements obliterated or abandoned. These initial effects are only the beginning, as the gases released will interact with the global atmosphere, potentially lowering temperatures and disrupting climate patterns for years to come. Even within the eruption, smaller details illustrate the complexity of the event. Pyroclastic surges may carve channels through the landscape, traveling over hills and around obstacles. Ash clouds can rise unevenly, creating areas of heavier deposition that may be far from the main vent. Molten rock fragments, or volcanic bombs, may fall for kilometers around the eruption, leaving scars and new landforms. Hot gases and particles can travel above the ground, igniting forests and spreading destruction beyond the immediate reach of lava. These effects demonstrate the dynamic, unpredictable nature of supervolcanic eruptions and the breadth of their influence. Finally, the visual and environmental drama of an eruption is matched by the scientific insight it provides. Observing the flow of magma, the dispersal of ash, and the spread of gases allows scientists to reconstruct past events and anticipate future behavior. Each eruption, though catastrophic, adds to the understanding of supervolcano mechanics. Patterns emerge: how pressure builds, how gases escape, and how magma viscosity influences explosiveness. These lessons are critical for assessing risk and preparing for the possibility of future eruptions. Through careful observation, the violence of a supervolcano becomes not just a display of destruction, but a source of knowledge about the planet's inner workings. When a supervolcano erupts, the immediate area suffers the most intense consequences. Within a radius of 1,000 kilometers, the landscape is transformed almost instantly. Pyroclastic flows surge outward from the vent, dense clouds of gas, ash and rock moving at speeds that can exceed several hundred kilometers per hour. These flows are lethally hot, reaching temperatures above 800 degrees Celsius, and they flatten forests, sweep away buildings, and ignite fires across every surface they touch. The sheer force and speed of these flows leave little chance for life to escape in the closest zones, turning thriving landscapes into ashen wastelands in a matter of hours. Lava flows accompany pyroclastic surges, though they typically advance more slowly. Their immense heat melts rock, destroys roads, and engulfs villages. The molten rock often follows valleys and low-lying areas, carving new paths through the terrain and leaving permanent scars on the earth. These flows solidify into new rock layers, reshaping the topography and altering river courses. Even after the eruption, the hardened lava acts as a barrier to regrowth, requiring decades or centuries for ecosystems to re-establish themselves over the newly formed surfaces. Earthquakes are common before and during the eruption, caused by the movement of magma and the fracturing of the crust. These tremors can collapse buildings, bridges, and other structures far beyond the immediate caldera. The combination of shaking, fire, and falling debris intensifies the destruction. Infrastructure collapses not only from the direct force of pyroclastic flows, but also from the shaking that weakens walls, roads, and power lines. Water and energy systems are disrupted, leaving survivors without access to essential resources, while transportation networks crumble, preventing escape and aid from reaching affected areas. Human mortality is staggering in such events. In historic eruptions, such as Mount Tambora in 1815, tens of thousands of people perished from pyroclastic flows, ash inhalation, and starvation caused by disrupted agriculture. The speed and temperature of the flows allow few to survive within the immediate zone. Even those outside the most extreme zones face danger from ashfall and collapsing structures. Communities are often obliterated within hours, leaving few signs of habitation. Survival depends on rapid movement away from danger zones, availability of shelter, and access to uncontaminated water and food. Mortality estimates in these areas can reach near total in the first days of a super-eruption. The geological aftermath is visible almost immediately. Craters form where the ground collapses into emptied magma chambers, sometimes spanning tens of kilometers across. Land subsides gradually as the crust adjusts to the absence of support beneath it. Valleys sink and ridges crack or tilt. Rivers may be dammed by lava or ash, creating temporary lakes. Existing lakes may be filled with volcanic debris or drained as the terrain changes. The ground becomes unstable, with fissures and landslides common for years after the eruption. These changes are permanent and fundamentally alter the topography of the affected region. Ashfall is among the most widespread hazards. Fine particles carried by wind can reach hundreds or even thousands of kilometers from the caldera. The ash covers roads, roofs, and fields, collapsing structures under its weight and smothering vegetation. For humans and animals, inhaling ash is deadly, causing respiratory distress and, over time, lung failure. Visibility drops to near zero during heavy ashfall, turning day into night. The sound of the eruption, rumbling, explosions, and the roar of pyroclastic flows is overwhelming, creating a sensory experience of fear and awe. The smell of sulfur and scorched earth fills the air, while hot gases burn the skin and eyes, leaving the surrounding environment hazardous even for those who survived the initial blast. Forests, grasslands, and wetlands within the affected radius are flattened or buried. Trees are snapped or scorched. Plants are coated with ash, and soil chemistry is altered by acidic deposits. Animals are killed outright or forced to flee, disrupting food chains. In rivers and lakes, ash and debris suffocate aquatic life. The immediate ecological damage mirrors the human and infrastructural losses, creating a silent, desolate landscape that bears the imprint of sudden, immense energy released from below. Firestorms often follow the eruption in the surrounding region. Hot pyroclastic flows ignite forests and grasslands, while falling volcanic bombs start fires across valleys. The combination of ash and heat makes it nearly impossible to control these fires, which can merge into extensive burn zones. Smoke and ash from these fires combine with volcanic emissions, darkening the sky further and worsening air quality. Survivors outside the initial blast zone face danger from secondary fires, exposure to smoke, and lack of clean water and food, creating a cascading series of threats that extends well beyond the vent. The sensory impact of the eruption is profound. The sky darkens under thick clouds of ash and dust, sunlight filtered into an eerie grey. A constant roar fills the air as pyroclastic flows and explosions tear through the landscape. The ground trembles beneath every step, and the air is hot and acrid. Ash coats every surface, turning familiar landscapes unrecognizable. In some places, the heat is intense enough to ignite clothing, vegetation, and wooden structures. Rivers of lava glow ominously at night, adding a red-orange light that contrasts sharply with the grey ash cloud. Even those who survive the initial blast experience disorientation, fear, and the overwhelming presence of natural forces that exceed human comprehension. Infrastructure collapses under multiple stresses. Buildings weakened by earthquakes fall under the weight of accumulating ash. Bridges and roads crack and sink into fissures. Power lines are severed, cutting communication and electrical supply. Water systems fail as pipes burst or become clogged with debris, and transportation becomes nearly impossible. Emergency response is delayed or impossible, compounding the effects of the eruption. Hospitals, schools, and government buildings are often destroyed or rendered unusable, leaving communities to fend for themselves amid the chaos. Human settlements within 1,000 kilometers are profoundly affected. Cities may be partially or completely buried under ash and debris. Rural communities experience crop loss, water contamination, and isolation from supply routes. Survivors must contend with the immediate hazards of ash, fire, and collapsed structures, while facing the longer-term consequences of disrupted food and water systems. Historically, eruptions like Toba and Tambora illustrate the rapidity and intensity of destruction, showing that modern technology, while helpful, cannot prevent the sudden and total impact within the immediate zone. Even after the eruption begins to subside, hazards continue. Ash continues to fall. Rivers carry volcanic debris downstream, and unstable ground collapses into new fissures. The heat from pyroclastic deposits can ignite secondary fires for days. Landslides occur as water interacts with loose volcanic material, reshaping slopes and valleys. Contaminated water and buried vegetation create toxic zones. Recovery is slow and dangerous, as the ground itself remains unstable, and the air carries fine ash particles that pose health risks. The initial eruption is only the beginning of a long, hazardous period in the local environment. The local ecosystem, human society, and geology are forever altered. Craters and calderas mark the sites of violent collapse, while rivers and valleys are redirected or buried. Forests are replaced by barren slopes, lakes may appear or vanish, and soil chemistry is changed by acidic deposits. Human and animal populations are reduced drastically. Roads, homes, and infrastructure may be permanently lost. Even after centuries, scars remain visible, telling the story of power released from deep within the earth. In this sense, the eruption is both destructive and transformative, reshaping not only the physical land, but also the patterns of life, movement, and survival in the affected region. Once a supervolcano releases its massive eruption, the effects are not confined to the area near the caldera. vast quantities of ash and fine particles rise high into the atmosphere, reaching the stratosphere tens of kilometers above the Earth's surface. At this height, winds can carry the particles across continents, spreading a layer of dust that reduces the amount of sunlight reaching the ground. The ash itself is composed of tiny fragments of rock and volcanic glass, light enough to remain suspended for months, yet dense enough to scatter and absorb sunlight. Alongside ash, gases such as sulfur dioxide form aerosols, small droplets that linger in the upper atmosphere and intensify the cooling effect by reflecting sunlight back into space. This process can trigger a volcanic winter, a period of reduced global temperatures caused by the blockage of sunlight. When sunlight is diminished, the energy reaching the Earth's surface drops, and the air and oceans begin to cool. Temperatures can fall by several degrees, enough to disrupt seasonal patterns. Frosts may occur during summer months in some regions, shortening growing seasons and stressing ecosystems that depend on predictable weather. The cooling effect is more pronounced at higher latitudes but can influence weather systems worldwide, changing the timing and intensity of storms, precipitation, and wind patterns. The stratospheric aerosols remain for months to years, prolonging the effect and spreading it beyond the eruption's immediate hemisphere. Historical eruptions provide concrete examples of these global climatic consequences. The Toba eruption, approximately 74,000 years ago, released enormous quantities of ash and sulfur dioxide into the atmosphere. Geological evidence suggests that the eruption caused a significant drop in global temperatures, potentially by as much as 6 to 10 degrees Celsius. The volcanic winter may have lasted several years, resulting in reduced plant growth, diminished food sources, and severe challenges for human populations and other species. Although the exact impact on early humans remains debated, it is clear that such an eruption had profound effects on both climate and life. Smaller eruptions, while less extreme, still offer insights into volcanic influence on climate. The 1883 eruption of Krakatoa, for example, produced spectacular sunsets and lower global temperatures for several years. Ash and aerosols circulated the globe, creating measurable climate effects, even though the eruption was much smaller than a supervolcanic event. These examples demonstrate that volcanic activity can act as a natural experiment, showing how suspended particles and gases in the upper atmosphere alter energy balance and climate patterns over wide regions. The cooling effects extend to ocean currents and precipitation patterns. As the surface temperature drops, the movement of water in oceans slows, changing currents that distribute heat across the planet. This can affect monsoons, rainfall in tropical regions, and the frequency of storms in mid-latitudes. Precipitation may decline in some areas and increase in others, creating droughts or floods in unexpected places. Rivers and lakes respond to these shifts, influencing ecosystems dependent on stable water sources. Even temporary changes in ocean temperature can disrupt the migration patterns of fish and marine mammals, affecting food availability for human populations relying on marine resources. Seasonal cycles are also affected by the volcanic winter. Spring may arrive late, summers may remain cold, and winters may extend longer than usual. Crops planted at traditional times may fail, and animals dependent on seasonal cues for breeding or migration may struggle to survive. The delicate balance between daylight, temperature, and moisture is altered, causing cascading effects throughout ecosystems. These disruptions can last for several years if ash and aerosols persist in the stratosphere, creating a slow, pervasive change that extends far beyond the initial eruption. The scale of climate effects depends on the size of the eruption and the composition of magma and gases. High silica magma, rich in volatile gases, produces explosive eruptions that loft large volumes of material into the stratosphere. The more sulfur dioxide released, the greater the reflective effect on sunlight. Ash with fine particles remains suspended longer, contributing to a prolonged dimming of the sky. The combination of ash and aerosols can produce measurable cooling on a global scale, unlike localized eruptions that affect only the immediate region. Supervolcanoes, by their nature, have the potential to alter climate for multiple years, creating conditions that challenge life worldwide. The duration of climate effects following a supervolcano is substantial. In addition to immediate temperature drops, the deposition of ash alters soil chemistry and reduces sunlight for plants. Photosynthesis declines, affecting the growth of forests, grasslands, and crops. Reduced vegetation further changes the composition of the atmosphere, limiting the exchange of carbon dioxide and oxygen. Ocean ecosystems are affected as well, with cooler surface waters slowing biological activity and altering plankton populations that form the base of the marine food chain. These effects ripple through terrestrial and marine ecosystems, demonstrating the interconnectedness of climate, life, and geological activity. Volcanic aerosols also influence weather systems by interacting with clouds. They provide nuclei for condensation, which can increase cloud cover and change rainfall distribution. In some regions, rainfall may increase, causing floods and erosion, while in others it decreases, leading to drought. The timing of these changes is not uniform. Some areas experience immediate effects, while others feel the impact months later as aerosols circulate through the stratosphere. This uneven distribution complicates forecasting and human response, requiring careful study of atmospheric dynamics and the transport of particles. The sun's light is altered not only in intensity, but in quality. Ash particles scatter shorter wavelengths of light, often giving sunsets a red or orange hue that is more vivid than usual. This change in sunlight can be observed worldwide, providing a visual signal of the ongoing volcanic influence. The presence of volcanic haze affects daily life, from reduced visibility for transportation to health hazards from inhaling fine ash particles. Even in regions far from the eruption, the sky may appear dim, and solar energy availability may decline, affecting agriculture, energy production, and ecosystems dependent on sunlight. The combination of ash and gases in the stratosphere can also affect the chemical balance of the atmosphere. Sulfur dioxide interacts with water vapor to form tiny droplets of sulfuric acid, which persist as aerosols. These droplets contribute to cooling by reflecting sunlight, but also produce acid rain when they eventually fall to the surface. Acid rain damages plant leaves, contaminates rivers and lakes, and alters soil chemistry, further challenging ecosystems already stressed by lower temperatures and reduced sunlight. The environmental impact of a supervolcanic eruption, therefore, extends from the atmosphere down to the surface, influencing climate, water systems, and land productivity on a global scale. Taken together, these processes illustrate how a supervolcano can transform the global climate. Ash and aerosols block sunlight, temperatures drop, seasonal cycles shift, precipitation patterns change, and ocean currents respond to altered heat distribution. Historical eruptions confirm that these changes are not minor or localized, but can persist for years, affecting human populations, ecosystems, and the physical environment across continents. The eruption of a single supervolcano is capable of creating a prolonged period of climatic disruption that challenges the resilience of life on Earth. demonstrating the power of geological processes to shape the world far beyond the site of eruption. When a supervolcano erupts, the disruption extends far beyond the immediate area and into the systems humans rely on most: food and water. The ash and aerosols that fill the atmosphere reduce sunlight, cool the air, and alter precipitation patterns. Crops, which depend on predictable sunlight and seasonal cycles, are especially vulnerable. Photosynthesis slows as sunlight diminishes, reducing growth rates. Fields that once produced abundant harvests may fail entirely, leaving communities without sufficient food. Even a small decrease in sunlight can reduce the yield of staple crops like wheat, rice, corn, and potatoes. When multiple regions are affected simultaneously, the combined effect on global food supply is severe. The cooler temperatures brought on by volcanic winter extend frost conditions into seasons normally warm enough for planting and growing. Late spring frosts may damage newly sprouted crops, while early autumn frost can halt maturation before harvest. Frosts are uneven, affecting some regions more than others, but even partial damage can create shortages in areas that depend heavily on local agriculture. For farmers, these temperature changes are unpredictable, making planning difficult. In some regions, soil may remain frozen longer than usual, delaying planting and reducing the window for crops to mature before winter arrives. Reduced sunlight and lower temperatures are compounded by irregular rainfall. Ash in the atmosphere alters weather patterns, sometimes causing drought in one area and flooding in another. Crops are sensitive not only to heat, but also to water availability. Fields deprived of rain or oversaturated with water fail to produce reliable yields. The combination of shorter growing seasons, limited sunlight, and unpredictable precipitation places enormous stress on regional agriculture, creating the conditions for food scarcity and economic disruption. Soil chemistry may also change where ashfall is heavy, temporarily reducing fertility and making land less productive, until the ash weathers over months or years. Livestock, dependent on available feed, water, and shelter, also suffers. Pastures covered in ash become unusable, and fodder crops fail due to shorter seasons. Animals exposed to ash-laden environments can suffer from respiratory problems, poisoning, and lack of forage. Mortality rates among farm animals rise, reducing available protein and further compounding the problem for human populations. Domesticated species are at particular risk because they rely entirely on human-provided food and water. In addition to livestock, wild animal populations may decline as their habitats are altered, food sources diminish, and harsh weather persists longer than usual. Food security collapses unevenly but profoundly. Local shortages can quickly cascade into national or global crises. Regions that normally rely on imports are vulnerable if exporting areas are affected by reduced harvests. Prices for remaining food increase dramatically, making it inaccessible for lower-income populations. Historical evidence from smaller eruptions shows that even moderate volcanic events can produce famine if agricultural systems are stressed, and supervolcanoes would magnify these effects. The global interconnectedness of food supply means that disruptions in one area can ripple outward, threatening populations thousands of kilometers away from the eruption site. The timing of these disruptions follows a predictable sequence. Immediately after the eruption, ashfall may make local crops inedible and contaminate water sources. In the following weeks, stored food may sustain populations temporarily, but once that supply diminishes, scarcity becomes critical. Within months, shortages extend to regions where crops are dependent on sunlight for growth, affecting planting and harvest cycles. After a year, The most affected areas face severe food insecurity, with mortality rates rising if aid and alternative sources are unavailable. The timeline of scarcity can extend for several years, depending on the persistence of ash in the atmosphere and the length of the volcanic winter. Human populations adapt in some ways. Stockpiling of grains, vegetables, and water provides a buffer against short-term shortages. Greenhouses and hydroponic systems can extend the growing season indoors, using controlled light and temperature to bypass the limitations imposed by reduced sunlight. These systems, however, are limited in scale and resource-intensive, so they cannot replace large-scale field agriculture. Communities with robust food storage and alternative growing methods may survive the initial years better than those entirely dependent on conventional outdoor farming. Planning and preparation are crucial for reducing mortality and maintaining social stability during these periods. Local diets also change under conditions of scarcity. Communities may shift from nutrient-rich foods to whatever is available, relying on stored grains, root vegetables, or foraged wild plants. Livestock consumption declines as herds shrink. Malnutrition becomes a widespread concern, as calorie intake may drop even if small amounts of food are available. Vitamin and mineral deficiencies occur when diverse diets are no longer possible, weakening immunity and increasing susceptibility to disease. These secondary effects compound the direct threats posed by famine, creating a cycle that is difficult to interrupt without external support or intervention. Trade networks and supply chains play a critical role during volcanic winter. Areas less affected by ash and frost may attempt to supply affected regions, but transportation becomes difficult. Ash can block roads, collapse bridges, and disrupt shipping routes. Air travel may be grounded due to ash clouds, while rail and road transport are slowed or halted. Coordination is essential, yet during such global events, logistical challenges are enormous. Delays in distribution can mean that food reaches some populations only after critical shortages have already emerged. Over time, repeated crop failures challenge long-term survival. Farmers face uncertainty with each planting season, knowing that sunlight may remain insufficient or that frost events may destroy young crops. Soil covered by ash must be cleared or amended, sometimes requiring years for natural processes to restore fertility. Water sources may be contaminated with acid from volcanic gases or ash deposits, complicating irrigation and drinking supply. The combined pressure of these factors reduces agricultural productivity, creating a situation where societies must carefully manage available resources to prevent further collapse. In addition to direct crop and livestock loss, the eruption indirectly affects other components of the food system. Fishing is disrupted as ash and sulfur dioxide alter water chemistry in rivers and coastal areas. Insects and pollinators may decline due to reduced flowering and ash deposition, reducing yields for crops dependent on pollination. The interdependence of these elements demonstrates how a single geological event can cascade through multiple layers of human food production, threatening nutrition, economy, and survival on a broad scale. Adaptation strategies may vary by region. Northern regions, already limited by shorter growing seasons, are especially vulnerable to further cooling. Areas dependent on rain-fed agriculture face particular risk if precipitation patterns are altered. Societies with experience in subsistence farming or strong traditions of food preservation may fare better than highly industrialized regions reliant on global supply chains. Each society must respond based on local conditions, available technology, and historical experience with environmental stress. Human ingenuity can mitigate some effects, but only within limits imposed by the scale and duration of the volcanic event. Beyond the immediate years, the timeline of recovery is gradual. Volcanic ash slowly weathers into soil, restoring some fertility, while sunlight returns to normal once aerosols settle from the atmosphere. Agricultural productivity may resume, but the disruption of ecosystems, soil chemistry, and water systems delays full recovery. Livestock populations must be rebuilt, seed stocks replenished, and irrigation infrastructure repaired. The global food system is resilient but not immune. The severity of disruption depends on the magnitude of the eruption and the interconnectedness of affected regions. Recovery may take decades, even under optimal circumstances. Human experience during this period is characterized by careful rationing, reliance on stored food, and efforts to maintain planting cycles wherever possible. Nutrition is often compromised, and malnutrition-related illnesses increase. Communities may relocate to less affected areas, creating migration pressures that further challenge remaining agricultural and economic systems. Governments and aid organizations, if operational, provide assistance where possible, but the scale of a supervolcano eruption can overwhelm even well-prepared systems. Societal resilience is tested alongside agricultural capacity, showing that food security is a cornerstone of survival during these events. Ultimately, the agricultural and food security consequences of a supervolcanic eruption illustrate how deeply human society depends on stable environmental conditions. Reduced sunlight, frost events, disrupted precipitation, and soil changes all combine to threaten food production at local, regional, and global scales. Livestock mortality, crop failure, and cascading famine illustrate the fragility of our systems when faced with forces far beyond human control. While technology, stockpiling, and adaptive strategies can mitigate some effects, the scale and duration of a supervolcanic eruption make it one of the most serious natural threats to human survival, demonstrating that the ability to feed populations is tightly linked to the stability of Earth's climate and atmosphere. Human survival after a supervolcanic eruption depends on both the scale of the eruption and the preparedness of the population. Urban areas, densely populated with millions of people, face immediate challenges. Buildings may collapse under the weight of ash, roads and bridges may be impassable, and water and energy systems often fail. The sudden loss of basic infrastructure forces residents to rely on stored food, water, and medical supplies. High-rise buildings, while offering temporary shelter, may become dangerous if ash accumulates on roofs or if tremors destabilize structures. Streets covered in ash create hazardous conditions for movement, making evacuation difficult. Those who cannot leave face the combined risks of respiratory problems from ash inhalation, heat and fire hazards, and exposure to falling debris. Rural populations encounter a different set of challenges. They may be farther from the main blast zone, but they rely heavily on local agriculture for survival. Crop failures, frost events, and contaminated water can eliminate the food sources these communities depend upon. Livestock losses compound the problem, reducing both immediate nutrition and future food security. Rural areas may also be isolated due to damaged transportation networks, making it harder for aid to reach them. On the other hand, lower population density sometimes allows more flexibility in relocation and access to uncontaminated land for planting or foraging, though long-term survival remains dependent on resource availability and environmental conditions. Migration is a key response to supervolcanic events. People attempt to move away from heavily affected areas to zones where ashfall is lighter, temperatures are less disrupted, and water and food are accessible. Migration is not simple. Transportation networks are often impaired, and mass movement creates competition for limited resources in safer regions. Temporary shelters may be established in less affected areas, including public buildings, tunnels, or natural caves. These shelters must provide protection from ash, cold temperatures, and contaminated water. Those who cannot reach safe zones may remain in exposed regions, where mortality is likely to be high in the first days and weeks following the eruption. Resource distribution becomes critical to survival. Stored food, water purification systems, and fuel for heating or cooking must be rationed carefully. Governments, if functional, may coordinate relief efforts, but the scale of a supervolcanic eruption can overwhelm centralized systems. Local communities often organize their own distribution networks, sharing resources among neighbors. Social cohesion is a factor in survival. Groups that maintain order and cooperate tend to survive longer than those in which panic or conflict arises. Community planning, knowledge of local terrain, and access to uncontaminated water are decisive in maintaining life during the initial months after an eruption. Historical examples offer valuable lessons. The 1815 eruption of Mount Tambora in Indonesia resulted in a year without a summer, with widespread crop failure and famine across Asia, Europe, and North America. Populations dependent on local agriculture suffered starvation, while migration to less affected regions provided a survival strategy for some. In Europe, grain shortages led to riots and social unrest, showing how extreme environmental stress can challenge governance and social stability. Communities that stored food, shared resources, or adapted planting schedules fared better, illustrating the importance of planning and flexibility in response to sudden climate disruption. Social dynamics under extreme stress are complex. Panic can spread quickly, but cooperation often emerges as a critical survival mechanism. Groups that organize food collection, water purification, and shelter construction increase their chances of sustaining life. Conversely, competition for limited resources may lead to conflict, weakening overall survival rates. Communication networks, both formal and informal, become essential in coordinating efforts. Rumors and misinformation, however, can exacerbate stress and create dangerous decisions, highlighting the importance of accurate information even amid environmental chaos. Mortality rates vary depending on proximity to the eruption, availability of food and water, and shelter. Within the immediate blast zone, near-total mortality can occur within hours due to pyroclastic flows, heat, and asphyxiation. In areas affected by ashfall and volcanic winter, deaths increase gradually, primarily from starvation, exposure, and disease. In historical events like Tambora, famine caused tens of thousands of deaths over the course of months and years. A supervolcano eruption, much larger than Tambora, could potentially affect millions of people worldwide, with initial mortality concentrated locally and secondary mortality spread over years due to disrupted food systems, disease, and environmental stress. Medical care is limited in such events. Hospitals may be destroyed or inaccessible, and resources like antibiotics, clean water, and medical supplies become scarce. Minor injuries can become life-threatening, and common diseases can spread quickly in crowded shelters or among displaced populations. Mental health is also affected, as survivors cope with trauma, loss, and uncertainty. Social support, organization, and leadership play vital roles in maintaining stability, reducing panic, and increasing the likelihood of survival in affected communities. Long-term survival relies on the ability to adapt to a new environment. Agriculture may require relocation to safer areas, with the rebuilding of food systems taking years. Livestock must be restocked, and soil and water must recover from ash and chemical deposition. Communities must adjust to altered climate conditions, including colder temperatures, shorter growing seasons, and irregular rainfall. Societies with technology for indoor farming, greenhouse cultivation, or hydroponics have an advantage, but these systems are resource-intensive and limited in scale. Populations unable to adapt face prolonged periods of scarcity and high mortality. Population density affects survival outcomes. In sparsely populated regions, survivors may find greater access to uncontaminated water, fertile soil, and food from remaining crops or wildlife. In densely populated urban centers, survival is constrained by collapsed infrastructure, limited mobility, and reliance on stored food. Emergency response and aid distribution are more complicated when millions are concentrated in small areas. The interplay between population size, available resources, and environmental stress determines survival rates, emphasizing the importance of both planning and adaptability. Human resilience is evident in historical responses to environmental crises. Communities with strong social networks, shared knowledge, and flexible strategies often survive better than those without. In times of scarcity, human ingenuity emerges. Alternative food sources are sought, water is filtered, and shelter is improvised. Even in the absence of modern technology, survival strategies rely on observation, cooperation, and knowledge of local resources. These lessons suggest that while a supervolcanic eruption would be catastrophic, the ability of humans to organize, adapt, and innovate could reduce overall mortality compared to unprepared populations. Migration patterns may extend across continents as people flee heavily affected zones. Transporting resources and knowledge becomes critical, and the timing of movement is important. Moving too early may expose populations to initial ashfall and hazards, while moving too late may trap them in areas without access to food, water, or shelter. Populations that coordinate movement and establish temporary camps along safe routes increase survival probability. Historical famines illustrate that even with limited resources, coordinated migration and communal survival strategies can mitigate the worst effects of environmental stress. Finally, human survival is shaped by both environmental and societal factors. Proximity to the eruption, strength of infrastructure, availability of food and water, social cohesion, and adaptability all influence outcomes. Mortality is highest immediately after the eruption in areas closest to the vent, then declines over time as populations either adapt, migrate, or perish due to food scarcity and disease. In extreme scenarios, global population may be reduced by millions, yet local survival is possible where communities organize effectively, utilize resources wisely, and respond flexibly to changing conditions. This segment illustrates that while a supervolcanic eruption is an existential threat, human resilience, planning, and cooperation play decisive roles in determining who survives and how societies recover over months and years. The eruption of a supervolcano affects not only the environment and food systems, but also the health of human populations on a massive scale. The first and most immediate hazard is airborne ash. Fine particles of rock, volcanic glass, and minerals are carried by winds across continents, and when inhaled, they cause respiratory distress. For those living near the eruption, the air becomes thick with dust, and breathing becomes difficult even in sheltered spaces. Lungs struggle to filter out the small, sharp particles, leading to irritation, inflammation, and in many cases, serious respiratory disease. Chronic exposure can result in long-term damage, with survivors experiencing persistent coughing, reduced lung capacity, and heightened vulnerability to infections. The chemical composition of volcanic ash can worsen its effects. Sulfur dioxide and other gases released during the eruption mix with moisture in the air to form acid particles. Inhalation of these particles irritates the airways and increases the risk of bronchitis and pneumonia. Vulnerable populations, including children, the elderly, and people with pre-existing conditions, are at greatest risk. Hospitals and medical facilities may be overwhelmed or destroyed, reducing access to care and increasing mortality rates from otherwise treatable conditions. In urban areas, dense populations intensify exposure and transmission of respiratory illnesses, while rural populations face difficulty reaching medical help if they develop symptoms. Water contamination compounds the health risks. Ashfall can deposit heavy metals and acidic compounds into rivers, lakes, and reservoirs. Drinking water becomes unsafe, carrying both chemical toxins and microbial contaminants. Communities dependent on local water sources may face immediate shortages of clean water. Efforts to filter or purify water may be hampered by limited resources, equipment, and fuel. Crop irrigation is also affected, with contaminated water reducing the safety and nutritional quality of plants grown during and after the eruption. In some cases, crops may absorb harmful substances from volcanic ash, creating a secondary pathway for disease when consumed. Nutritional deficiencies emerge as global food systems collapse. Reduced sunlight, frost events, and disrupted rainfall diminish crop yields, limiting the availability of vitamins, minerals, and calories. Populations may survive on stored grains, root vegetables, and limited livestock products, but these foods often lack essential nutrients. Vitamin deficiencies weaken the immune system, increasing susceptibility to infections. Protein shortages and limited dietary variety compound the problem, particularly among children and pregnant women. Malnutrition becomes widespread in regions heavily impacted by ashfall and climatic cooling, creating secondary health crises even as the initial eruption subsides. Famine and displacement further increase vulnerability. As people migrate from affected areas in search of food and water, crowded shelters, camps, and urban centers become breeding grounds for infectious diseases. Cholera, dysentery, and other waterborne diseases spread rapidly when sanitation and clean water are inadequate. Respiratory infections compound these problems as ash-laden environments and overcrowding increase transmission. The combination of malnutrition, contaminated water, and infectious disease creates a dangerous cycle that can persist for months or even years after the eruption, particularly in areas with limited medical infrastructure. Psychological stress is another major health concern. Survivors experience trauma from the destruction of homes, loss of family members, and displacement. Anxiety, depression, and post-traumatic stress disorder are likely to increase in affected populations. Children may experience developmental delays due to nutritional deficits and stress. Societal disruption, including the collapse of local governance, law enforcement, and healthcare systems, exacerbates mental health challenges. Communities struggle to maintain social cohesion, and social unrest may arise when resources are scarce. Psychological stress, combined with physical health threats, further complicates recovery efforts. In addition to immediate health threats, long-term outcomes for survivors are profound. Respiratory damage may persist for years, requiring ongoing medical care. Malnutrition and dietary deficiencies during critical developmental periods can lead to lifelong cognitive and physical impairments. Survivors who experience repeated exposure to ash and volcanic gases may develop chronic respiratory conditions such as bronchitis, asthma, and emphysema. Mental health conditions can become chronic without access to support services, and social stressors may continue as communities rebuild under altered environmental conditions. Recovery requires not only rebuilding infrastructure, but also addressing long-term health and well-being. Epidemiological consequences are amplified by population movements. Displacement increases the risk of outbreaks in new locations, as previously unexposed populations encounter infected individuals or contaminated food and water. Immunity gaps in children and isolated communities can lead to higher morbidity and mortality from preventable diseases. Humanitarian interventions may mitigate some of these effects, but during a supervolcanic event, logistical challenges, destroyed infrastructure, and widespread environmental hazards hinder medical response. Coordination of aid, vaccination, and water purification becomes critical to prevent secondary health crises. Secondary hazards from environmental changes also affect health. Reduced sunlight, cooler temperatures, and ash-covered terrain limit the availability of natural food sources. Wild plants may be scarce or contaminated, and foraging becomes risky. Livestock shortages reduce protein intake, while fisheries may collapse due to ash deposition in rivers and coastal waters. These combined effects increase vulnerability to disease and malnutrition, particularly among populations that are already marginalized or living in precarious conditions. Health outcomes are intertwined with environmental recovery, highlighting the dependency of human survival on stable ecosystems and clean resources. Air quality remains poor for extended periods. Fine ash particles remain suspended in the atmosphere, sometimes for months, as wind circulates them globally. Even populations far from the eruption zone experience respiratory discomfort, eye irritation, and reduced outdoor activity due to poor air quality. Agricultural workers, emergency responders, and those living in exposed areas face the highest risk. Chronic exposure may lead to permanent lung damage, while acute exposure can be fatal in areas of dense ash deposition. Health monitoring and protective measures, such as masks and indoor air filtration, are essential for mitigating these effects, but their effectiveness depends on availability and proper use. The cumulative effect of these health challenges is a high overall mortality rate in the months and years following a supervolcanic eruption. Immediate deaths result from pyroclastic flows and ash inhalation, but secondary deaths from famine, disease, and malnutrition extend over years. Vulnerable populations, including children, the elderly, and those with pre-existing conditions, are most affected. Historical evidence from Tambora and other large eruptions shows that mortality continues after the initial event, often peaking months later when food shortages, water contamination, and infectious disease converge. Public health strategies, medical response, and social cohesion significantly influence these outcomes. Mental and social health interact with physical health. Communities that maintain organization, mutual aid, and communication tend to reduce panic and prevent conflict, allowing resources to be used efficiently. Where social order breaks down, mortality rates rise not only from physical causes but also from violence and neglect. Education, leadership, and local knowledge play a key role in mediating these effects, illustrating the interdependence of human behavior and health outcomes during extreme environmental stress. Health, survival, and social resilience are inseparable in these conditions. Long-term survivors face persistent health challenges as they rebuild communities. Soil contamination and water quality issues may continue for years, affecting nutrition and disease risk. Respiratory and digestive problems may require ongoing care, while mental health needs remain significant. Children born during or immediately after the eruption may experience developmental delays due to malnutrition and environmental stress. These challenges create intergenerational impacts, demonstrating that the health consequences of a supervolcano extend far beyond the immediate eruption and continue to influence human populations for decades. Preventive strategies and preparedness can mitigate some of these health impacts. Stockpiling clean water, food, and medical supplies provides a buffer against initial shortages. Shelters equipped to protect against ash and toxic gases reduce exposure. Rapid deployment of medical teams, water purification systems, and vaccination programs can limit the spread of disease. Education on the risks of ash inhalation, contaminated water, and malnutrition improves community resilience. While no strategy can eliminate the threat entirely, coordinated planning, public health interventions, and community cooperation significantly reduce mortality and long-term health consequences. In summary, the global health impacts of a supervolcanic eruption are multi-layered and enduring. Respiratory diseases from ash inhalation, water contamination, crop toxins, and malnutrition pose immediate threats. Displacement, famine, and disrupted social structures increase vulnerability to infectious disease. Psychological stress and societal disruption exacerbate physical health problems, while long-term effects continue for years. Survivors face a combination of environmental, nutritional, and social challenges, highlighting the interconnected nature of human health and the environment in the aftermath of catastrophic geological events. Understanding these impacts is critical to planning, response, and resilience in a world vulnerable to the immense power of supervolcanoes. The eruption of a supervolcano affects not only humans, but every living organism within its reach. Flora and fauna respond to the sudden environmental shock in complex ways. Heavy ashfall covers forests, grasslands, and wetlands, smothering plants and reducing sunlight necessary for photosynthesis. Many trees lose leaves or die entirely, while smaller plants struggle to survive beneath layers of fine ash. Soil becomes temporarily sterile in areas of thick deposition, and water sources are contaminated with acidic compounds, making survival for both plants and animals difficult. The immediate ecological impact can resemble a blackout across the landscape, with entire ecosystems collapsing under the weight of ash, chemical exposure, and disrupted climate. Animals respond with migration, adaptation, or mortality. Birds may attempt to fly beyond the affected region, but ash-laden skies and the scarcity of food complicate movement. Large mammals, including herbivores and predators, face the dual challenge of finding uncontaminated vegetation and avoiding environmental hazards. Insects and smaller organisms are especially vulnerable because their habitat and food sources are limited. Some species experience population collapse, particularly those that are specialized, slow reproducing, or already near the edge of survival. Rapid changes in temperature, sunlight, and precipitation place additional stress on sensitive species, threatening biodiversity across local and global scales. Soil recovery begins slowly once the eruption ends, but it is a gradual process that can take years or decades, depending on ash thickness, composition, and local climate. Volcanic ash is initially inhospitable, lacking organic matter and essential nutrients in forms plants can immediately use. Microorganisms such as bacteria and fungi start to recolonize the ash, breaking down minerals and creating conditions for plant growth. Pioneer species such as mosses, lichens, and hardy grasses establish first, stabilizing the soil and beginning the long process of ecological succession. These early colonizers gradually enrich the soil with organic matter, allowing more complex plant communities to take root over time. Water systems are also affected and play a critical role in recovery. Rivers and lakes may be temporarily clogged with ash, reducing oxygen levels and disrupting aquatic ecosystems. Fish and amphibian populations decline due to contamination and temperature changes, which further impacts predators that rely on these species. Once ash settles and waterways are restored, aquatic ecosystems slowly re-establish themselves. Microbes and algae return first, followed by small fish and invertebrates, and eventually larger fish and mammals, creating a layered recovery that mirrors terrestrial succession in complexity and timescale. Historical and geological evidence shows the scale and duration of recovery. Fossil records indicate that supervolcanic eruptions have caused temporary mass extinctions and long-term ecosystem restructuring. Following the eruption of Toba around 74,000 years ago, climate cooling and ash deposition created conditions that significantly altered local and regional species distribution. Many species survived, but populations shrank dramatically, showing how vulnerable biodiversity is to prolonged environmental stress. Modern eruptions, though smaller, also illustrate patterns of resilience and adaptation. After the 1991 eruption of Mount Pinatubo, for example, forests in the Philippines experienced partial die-off, but within a decade, pioneer species had recolonized the slopes, and a new ecological balance emerged, demonstrating the gradual but persistent power of natural recovery. Ecosystem stabilization is not uniform. Some regions recover quickly due to fertile volcanic soils and moderate ash deposition, while others remain barren for decades where ash is thickest or climates remain harsh. Plant communities re-establish themselves in stages. First, hardy pioneers. Second, shrubs and fast-growing trees. And eventually, mature forests. Animal populations recover in parallel, following the re-establishment of plant-based food sources. Predator-prey dynamics return gradually, often reshaping the composition of local fauna compared to pre-eruption conditions. Even as ecosystems recover, the landscape retains the imprint of the eruption, with altered topography, soil composition, and species distribution. Interconnectedness of species becomes evident during recovery. Loss of one species affects others in unexpected ways. Pollinators may disappear temporarily, limiting plant reproduction. Herbivores decline, reducing food for predators. Aquatic systems suffer when small organisms die, disrupting the food web from the base upward. Recovery relies on the simultaneous re-establishment of multiple species, demonstrating how fragile ecological balance can be. Even minor disruptions in one part of an ecosystem may amplify the consequences, delaying overall recovery and making ecosystems more sensitive to future environmental stress. Biodiversity is particularly vulnerable to supervolcanic events. Specialized species, those with narrow ecological niches, or those with limited mobility, face the highest risk of local extinction. Generalist species often survive and may expand their range during the recovery period, reshaping ecosystems. Genetic diversity is affected when populations shrink dramatically, increasing susceptibility to disease, climate stress, and future environmental disturbances. The eruption acts as both a destroyer and a filter, leaving the resilient and adaptable species to recolonize and repopulate the affected regions. Ash chemistry also influences recovery patterns. Nutrient-rich volcanic ash can eventually enhance soil fertility, supporting dense plant growth in the decades following the eruption. However, high acidity and heavy metal content initially suppress plant development, creating a lag in ecological renewal. The pace of regeneration depends on local rainfall, temperature, and the presence of surviving organisms that can recolonize affected areas. In some cases, ash can form protective layers that prevent soil erosion, aiding long-term stability once vegetation returns. Recovery is spatially heterogeneous. Mountainous areas may experience landslides and debris flows, reshaping habitats. Valleys and plains may accumulate thick ash layers, delaying plant establishment. Rivers and lakes may redirect or fill with sediment, changing aquatic habitats. These physical changes create new ecological opportunities and challenges, influencing which species survive and how they adapt. Over time, landscapes gradually stabilize, though some areas retain permanently altered topography, affecting local biodiversity for centuries. Insect populations are key to recovery. Pollinators, decomposers, and other small organisms facilitate nutrient cycling and plant reproduction. Their early return accelerates ecosystem renewal, supporting the succession of larger plants and herbivores. Birds and small mammals follow, feeding on insects and dispersing seeds. Larger herbivores recolonize areas once sufficient vegetation exists, followed by carnivores. Each stage depends on the previous, highlighting the delicate interdependence of life and the long-term consequences of ecological disruption caused by supervolcanic eruptions. Global biodiversity is interconnected through migration and dispersal. Species surviving in unaffected regions may recolonize impacted zones, contributing to genetic diversity and ecosystem stabilization. Islands and isolated regions are particularly at risk, as recolonization opportunities are limited. Continental-scale eruptions affect larger areas, further testing the resilience of global biodiversity. Even species considered common may experience local extinction, illustrating that no ecosystem is entirely insulated from catastrophic geological events. The pace of ecological recovery is slower than human perception. While vegetation may reappear within years in some areas, full restoration of pre-eruption biodiversity and ecosystem function may take decades or longer. Complex food webs, predator-prey relationships, and plant-animal interactions require time to rebuild. Some species may never return, while others adapt to new conditions, creating ecosystems that are altered yet functional. The memory of the eruption remains embedded in species composition, soil characteristics, and landscape structure, demonstrating the lasting influence of supervolcanic events on life. Interactions between terrestrial and aquatic ecosystems further complicate recovery. Runoff from ash-laden soils can enter rivers and lakes, altering nutrient balances, oxygen levels, and water chemistry. Aquatic organisms respond according to their tolerance, with sensitive species declining and resilient species dominating. This affects fish populations, aquatic invertebrates, and birds that depend on these habitats for feeding and breeding. Recovery in one system influences the other, highlighting the interconnectedness of global biodiversity and the cascading impacts of a single catastrophic eruption. In summary, supervolcanic eruptions disrupt ecosystems on multiple levels: terrestrial, aquatic, and atmospheric. Flora and fauna experience mortality, migration, and adaptation. soil recovers gradually as microorganisms and pioneer species re-establish, eventually allowing more complex ecosystems to develop. The fossil record and modern eruptions provide evidence of these processes, showing how life persists despite extreme stress. Biodiversity remains vulnerable, but ecological succession, interconnected species interactions, and dispersal mechanisms allow recovery over years to decades. The process is slow, uneven, and shaped by both environmental conditions and species resilience, illustrating the profound and lasting influence of supervolcanic activity on life across the planet. Humanity today has developed tools to observe, measure, and sometimes anticipate the behavior of supervolcanoes, though predicting a full-scale eruption remains highly uncertain. Modern science relies on a combination of seismology, satellite imaging, and ground-based gas sampling to monitor volcanic activity. Seismographs detect small earthquakes and tremors beneath the surface, which often indicate magma movement. These signals provide clues about changes in pressure and potential eruptions. In supervolcanoes, the scale of underground magma chambers is immense, and subtle shifts may occur decades before any visible surface activity. By carefully analyzing seismic patterns over time, scientists aim to detect early warning signs that might allow for timely preparation. Satellites add a global perspective, observing heat patterns, ground deformation, and gas emissions over vast areas. Thermal imaging can identify regions of increased heat flow, signaling magma movement close to the surface. Ground swelling, caused by magma pressure beneath the crust, is monitored with radar and laser technology from space. Even minor elevation changes over thousands of square kilometers can indicate increasing pressure in the magma chamber. Satellite data is combined with ground measurements to produce models of risk and to forecast potential scenarios. While these methods cannot predict an exact eruption date, they improve understanding of volcanic behavior and help guide monitoring strategies. Gas sampling from volcanic vents, fumaroles, and the surrounding environment provides critical information about the chemical changes occurring beneath the surface. Supervolcanoes release gases such as sulfur dioxide, carbon dioxide, and hydrogen sulfide, which often increase in concentration prior to an eruption. Tracking changes in gas composition and emission rates can offer early signals of rising magma or destabilized pressure within the crust. Gas measurements also inform scientists about the potential atmospheric impact of a future eruption, including effects on climate, air quality, and human health. Continuous monitoring is necessary because gas emissions can fluctuate daily, requiring sustained observation to identify meaningful trends. Risk assessment combines these scientific observations with historical and geological records. While supervolcanoes are rare, the consequences of a large eruption are enormous, prompting extensive study. Geological evidence, including deposits from past eruptions, helps estimate the magnitude and frequency of events. For example, the Yellowstone supervolcano in the United States and Toba in Indonesia are studied in detail because of their massive scale and potential global impact. Scientists estimate that the probability of a supervolcano eruption in any given century is low, yet the potential for catastrophic consequences keeps attention focused on these systems. Probabilistic models guide government planning and scientific prioritization, balancing the rarity of the event against the severity of potential outcomes. Emergency planning is central to mitigating risk. Authorities develop evacuation routes, stockpile essential supplies, and coordinate with local, national, and international agencies. Population centers near known supervolcanoes require detailed contingency strategies to move people quickly and safely, in the event of rising seismic activity or venting of gases. Transportation networks, shelters, communication systems, and medical resources are mapped and maintained to maximize efficiency during a crisis. Scenario simulations allow planners to identify potential bottlenecks and challenges, such as ash-blocked roads, collapsed bridges, or overwhelmed healthcare facilities, so that mitigation strategies can be tested and improved before disaster strikes. Global coordination is increasingly recognized as essential. Volcanic eruptions do not respect national borders. Ash clouds, climate effects, and food system disruptions extend across continents. International organizations, scientific networks, and aid agencies collaborate to share data, research findings, and response strategies. Satellite information is distributed worldwide, enabling real-time monitoring and early warning for affected regions. Coordination also ensures that medical aid, food relief, and logistical support can be mobilized rapidly across borders. Collaboration reduces duplication of effort and maximizes the effectiveness of interventions, reflecting the global nature of both the hazard and the response. Technological solutions play an important role in preparedness. Remote sensing, predictive modeling, and early warning systems allow for faster identification of emerging threats. Agricultural technologies such as greenhouses, hydroponics, and controlled environment farming provide alternative food production methods when sunlight is reduced and crops fail outdoors. Water filtration, respiratory protection, and portable shelters increase resilience for populations at risk from ash, contaminated water, and cold temperatures. While technology cannot prevent a supervolcanic eruption, it can mitigate the worst effects, buying time for evacuation, rationing, and strategic allocation of resources. Investment in research and development enhances both monitoring capabilities and survival potential. Governments and agencies are central to preparedness. National emergency management organizations coordinate local responses, while international bodies, including the United Nations and global disaster relief networks, provide support for large-scale planning and post-eruption response. Policy decisions, funding for monitoring programs, and public education campaigns ensure that populations are aware of risks and can take action to reduce harm. Governments also facilitate research, share geological data, and support modeling efforts that improve understanding of supervolcano behavior. The combination of scientific monitoring, logistical planning, and international cooperation forms a network of preparedness designed to reduce casualties and societal disruption. Public awareness complements scientific monitoring. Education about volcanic hazards, emergency procedures, and personal preparedness measures is essential for effective response. Populations living near active or potential supervolcanoes benefit from drills, communication protocols, and accessible resources such as shelters and supply caches. Awareness campaigns explain the importance of clean water, respiratory protection, and safe food storage during ashfall or climate disruption. Informed communities are better able to cooperate, reduce panic, and maintain social order during the crisis, improving the chances of survival for individuals and society as a whole. Despite all technological and institutional advances, uncertainties remain. The complexity of supervolcano systems, combined with the rarity of eruptions, makes precise prediction extremely difficult. Scientists continue to refine models, integrate new data, and study past events to improve forecasting. Monitoring is continuous and multi-layered, yet no system can provide absolute certainty. Planning emphasizes resilience, preparing for low probability but high impact scenarios through stockpiling, infrastructure reinforcement, and contingency strategies. Preparedness is thus both a scientific and social endeavor, blending observation, modeling, policy, and public engagement to reduce potential harm. Finally, modern preparedness demonstrates the interconnectedness of science, technology, and governance in responding to natural hazards. Monitoring systems detect signs of unrest, predictive models estimate potential outcomes, and emergency planning organizes human response. Governments, organizations, and global agencies work together to coordinate logistics, provide aid, and educate the public. Technology offers tools to mitigate effects, while social cooperation ensures that resources are distributed efficiently. Although supervolcano eruptions are rare, these combined efforts illustrate how humanity can use knowledge, innovation, and organization to reduce the threat of one of Earth's most powerful natural forces. As the Earth moves slowly beneath our feet, humanity is reminded of the scale and power of the forces that shape the planet. Supervolcanoes are a quiet, hidden reminder of the vulnerability inherent in human existence. Unlike storms or earthquakes, their processes unfold over decades or centuries, largely invisible to everyday life, yet capable of altering climate, ecosystems, and societies in profound ways. Observing these systems through the lens of science provides a clear understanding of the magnitude of natural events compared with human capabilities. Even with all the technology, knowledge, and organization that modern society possesses, the raw energy stored beneath the crust remains beyond our control, a force indifferent to human intention or ambition. The vulnerability of humans to geological forces becomes more apparent when considering the scale of impact. Supervolcanic eruption can blanket thousands of square kilometers in ash, cool the climate globally, and disrupt food systems for years. Urban centers, reliant on centralized infrastructure, are particularly exposed to cascading failures, while rural populations face the challenge of survival with limited access to healthcare, food, and clean water. Historical events illustrate how quickly local and regional societies can be destabilized by volcanic activity, even at smaller scales. In this context, humans occupy a fragile position where adaptation is necessary for survival, but success is never guaranteed. Yet, alongside this vulnerability is the evidence of human adaptability. Populations have responded to volcanic eruptions, climatic shifts, and ecological stress through migration, cooperation, technological innovation, and planning. The establishment of monitoring networks, predictive models, and global coordination demonstrates the ability of societies to prepare for rare but high-impact events. Historical experience shows that knowledge, foresight, and organization can reduce mortality, maintain social cohesion, and preserve critical systems. Supervolcanoes do not render humans powerless, but they do test the limits of resilience, requiring both immediate response and long-term strategic thinking. The contrast between human adaptability and planetary processes emphasizes scale. Geological time operates on spans that exceed human lifetimes, while supervolcanoes accumulate energy slowly over tens of thousands of years, only to release it in moments of catastrophic change. This duality places human planning in a broader perspective. Even the most carefully constructed emergency systems are small-scale interventions in comparison to the energy of the Earth. Awareness of this imbalance fosters a form of humility, highlighting the need for preparation, observation, and respect for forces beyond our immediate perception. Scientific study of supervolcanoes provides lessons that extend beyond the technical. The observation of past eruptions, climate responses, and ecological recovery offers insight into thresholds of survival. understanding how food systems collapse under reduced sunlight, how human health deteriorates under combined stresses of malnutrition and disease, and how ecosystems gradually recover informs strategies for mitigation. Knowledge of these thresholds allows societies to anticipate challenges and design interventions that maximize survival. At the same time, the magnitude of the hazard reminds us that absolute control is impossible, reinforcing the importance of resilience rather than complacency. Preparedness, informed by observation and research, is a practical response to an unpredictable world. Stockpiling essential resources, establishing evacuation routes, and developing technologies for food production under adverse conditions are tangible expressions of this foresight. Equally important is the recognition of social factors. Cooperation, communication, and social cohesion enhance survival prospects in ways that technical solutions alone can achieve. Populations that maintain organization and trust are more likely to navigate the consequences of an eruption successfully, reflecting the interplay between knowledge, planning, and human behavior in extreme circumstances. The lessons of supervolcanoes extend into broader philosophical reflection. They demonstrate that humans exist within a planet governed by forces far larger and older than any society or civilization. The slow build-up of magma over tens of thousands of years, the sudden release of energy, and the prolonged environmental impact illustrate the scale of natural processes relative to human lifetimes. In studying these events, scientists develop a dual perspective, one that appreciates both the fragility of human systems and the capacity for intelligent adaptation. This perspective encourages a balance between respect for natural forces and the use of knowledge to reduce vulnerability. Ecological recovery after a supervolcano also offers insight into resilience. Life persists even in the face of extreme disruption. Pioneer species establish themselves on barren ash. Microorganisms slowly enrich the soil, and animal populations gradually return as food sources recover. These processes, operating over years or decades, demonstrate the inherent adaptability of life on Earth. Human societies can draw inspiration from these patterns, understanding that persistence, incremental recovery, and adaptation are central to survival in challenging conditions. Observation of ecological succession provides a framework for thinking about societal and technological recovery in parallel with environmental stabilization. Humility arises not only from recognizing vulnerability, but also from acknowledging the limitations of knowledge. Even with advanced monitoring and sophisticated models, the timing and scale of supervolcanic eruptions cannot be predicted with certainty. This uncertainty reinforces the importance of flexible strategies, redundancy in critical systems, and the maintenance of social and technological resilience. Human ingenuity is powerful, but it operates within constraints imposed by natural laws, physical energy, and planetary scale processes. Accepting these limits does not weaken human endeavor. Rather, it informs realistic planning and measured preparation. A supervolcano reminds us that resilience involves both immediate action and long-term thinking. Short-term responses, such as evacuation, medical care, and sheltering, are crucial during and after an eruption. Long-term strategies include rebuilding food systems, restoring health, and maintaining social cohesion. Scientific knowledge enables anticipation of hazards, but resilience emerges from the combination of foresight, adaptability, and cooperation. The interplay between preparation, observation, and responsive action defines humanity's capacity to survive extreme geological events. Finally, the reflection on supervolcanoes highlights a broader lesson about living on an active planet. Awareness of the forces that shape our world encourages both caution and responsibility. Preparedness, grounded in scientific understanding, enhances survival while fostering a deeper respect for the natural environment. Humanity's ability to endure such events depends not solely on technology or resources, but on planning, social organization, and knowledge applied wisely. The study of supervolcanoes teaches that survival is possible when humility guides action, foresight informs strategy, and adaptability governs response. By combining awareness with practical preparation, societies can navigate the challenges posed by Earth's most powerful geological forces and emerge resilient in the face of uncertainty.